Alright, back to the 2008 Suzuki SX4. I talked to the shop some more, to the technicians here. They said this one here, the engine is knocking, but this one runs. So I'm going to see, I check the oil, there's oil in it. Let's see how this one runs. If it starts, there's plenty of gas in it. It sounds terrible, but so mechanically it sounds terrible, but it revs up fine. So we have known good waveforms right here in this car if we need them, compared to that one. So let's I'm gonna put some gas in that one. That one seems to be running on empty, just to make sure we have a good fuel supply, and we'll keep going. It really sounds on that one that the engine's like constipated. If you full throttle it and it barely, you know, it'll get up to 4,000 RPM, but it struggles to get past 2,000, and then it kind of revs up. Yeah, pretty crazy. Alright, we got a good fuel supply now. Third of a tank. So fires right up. Seems to idle pretty happy. Let me just wait for it a little bit. Press the gas. So it almost hits a wall. Nuts. Alright, well, that's what it does. Let's compare it to the good car. We're going to use the scope. What measurements do we want to take? Alright, so first thing I'm going to do, I took the upstream oxygen sensor out. Let's just run it, see if it revs at all. My gut says it's a back pressure problem, but the scope showed it was not. The in cylinder. Nope, doesn't want to rev. Huh. Alright, so the quickest way to verify timing between a known good and a suspected mystery car is to do the exact same measurement we did yesterday. So channel 1 is on the camshaft sensor, channel 2 is on ignition coil number 1 trigger, channel 3 is on in cylinder number 1. Exact same measurement. We're going to compare apples to apples here. Fire this thing up. And here we go. That's all we need. Let's compare apples to apples. Alright, so here's the known good waveform. I got the 720 degree rulers, and here we see our valve timing, and I want to focus on the ignition timing and this cam pulse right here, this single pulse before the double pulse. So right here we see minus 38 degrees from top dead center. I can make it even a little more precise. Right there and right there. 40. We want to be exact to the degree. So line up your rulers really well. And that line is right there. So 42 degrees before TDC on number 1, this cam pulse. The ignition pulse starts at exactly the falling edge of the cam pulse and ends at 26 degrees. So 42 and 26, remember those numbers. Let's go to our suspected bad patient. That's our known good. This is our suspected bad. Let's line up the cursors. Right there and right there. So first measurement on the cam pulse, minus 17 degrees instead of minus 42. Okay, we're getting somewhere now. And the ignition is minus 13 instead of minus 26. So something is definitely off here by over 20 degrees, like 25 degrees. Let's take a look at a picture of the cam sprocket, count the number of teeth, and see how many degrees per tooth there is. Alright, here's where you need a notebook. So for the good engine, well, good and timing wise, our single cam pulse occurred 42 degrees before top dead center of cylinder 1. Spark pulse occurred 26 degrees before top dead center. On the bad engine, the one that is supposedly out of time, our cam pulse, single cam pulse, occurred 17 degrees before top dead center, and the spark occurred 13 degrees before top dead center. Let's verify that. So right there, minus 17, minus 13, that's the blue trace is minus 17 from TDC, the red trace is minus 13. So the spark timing can change according to the computer, but the cam timing should not change. This is not a VVT engine. This should be fixed. So it looks like on the bad engine we're 25 degrees retarded on the CMP pulse. And that is that on the intake or exhaust cam? I think that's on the exhaust, but let me double check. 13 degrees retarded on the spark compared to known good. Now the cam sprocket itself, here's what it looks like. There are 24 teeth. You can count them yourself. And one cam revolution is 720 degrees of the crank. So we know that for a 4-cycle engine, 720 divided by 24 teeth is going to give us 30 degrees per tooth. Okay? Now, that's not quite 25, is it? It's a little bit more per tooth. So are we one tooth off on the bad engine? Keep in mind, this engine, the one that's blown up here but the timing's still good, has 208,000 miles on it in original timing chains. The broken one, the bad timing engine, has brand new timing chains. So that 5-degree difference can be just attributed to a new chain versus a stretch chain. It's not as retarded, so if we stretch that chain, it would be 30 degrees retarded instead of 25. So I think we're a tooth off. For sure, there are 2 chains though, so that adds a little bit of complication. Let me look up the crank sprocket and the idler gear, which can change the ratios. Keep that in mind. But like, we're done. This thing needs the timing reset. The shop here, they let their rookie technician put it together, and like I said, this is not as straightforward as some vehicles. It has 2 chains, it has an idler, it has colored links and arrows, so I'm not surprised that it could be a tooth off, even though they said they verified it. I think it's, you know, is it off on both cams? We can see on our in-cylinder pressure waveform if all of the valve timing events are shifted, you know, 30 degrees to one side or another. I think they set the secondary chain, this one, you know, the secondary chain, they said these lined up, but if we're off a tooth on here, you know, this little idler, or a tooth off on the big side of the idler, yeah, it still could be about 25 to 30 degrees off on the crankshaft. So we're done. This thing needs timing chains reset. Looking up some more pictures, thank you to Rock Auto. There's a crankshaft sprocket. It's also 24 teeth, and then the idler right here, it's 18 teeth going to 36 teeth. Again, you can count them yourself. So as you can see, the crank turns the big pulley to 36 tooth, and then it reduces 2-to-1 ratio, so the camshafts spin at half the speed of the crank, obviously. It goes 36 to 18. So let's do a little thought experiment here. What if this idler is off 1 tooth on the chain? Okay, so we can do the same calculation. We can do 720 divided by 36 and 720 divided by 18. So what if the smaller chain is off 1 tooth on the idler, not on the cam, on the idler? So 18 divided by, or 720 divided by 18 is 40 degrees per tooth. 720 divided by 36 is 20 degrees per tooth. So we have 40, 20, and 20, and 30, 20, 30, 40, and we're off 25 degrees. We're retarded by 25 degrees. So I believe it's going to be, the chain is going to be off 1 tooth on the crank, and the main crank sprocket. Okay? So if this wasn't lined up, it was 1 tooth off, it would be equivalent to both of these cams being 1 tooth off, correct? Well, let's be careful here. The crank spins 360. So if you're 1 tooth off on the crank, you'll be 360 divided by 24, not 240 divided by 24, right? So 360 divided by 24, you'd be 15 degrees off. If you're 1 tooth off here, but they're 25, so it gets confusing really quickly. All we know is the timing is off, the timing cover has to come off, and we have to reset this crap. But I'm just curious if we can determine this precisely using the data we got from the oscilloscope and some pictures of the parts. Alright, let's pick a point for valve timing here. When does the intake valve close on the known good engine? So right here, you can see kind of a inflection point. That's when the valve physically closes and the pressure starts building inside the cylinder. So I'm going to put my cursor right there, right at that inflection point. We're at 608 degrees. Let's compare apples to apples. On the bad cylinder, see this inflection point right here? We'll say right about there, 635 degrees. So that's that 25 degree difference. So our intake valve is closing too late, so the engine isn't getting enough charge. And check out the peak pressure here, 45 psi on the bad engine and 70 or 85 on the good engine at idle. Huge difference. So we know the intake cam is 1 tooth retarded, too late. What about the exhaust cam? Can we say when the exhaust valve opens and closes? We can try. So on the known good, piston's coming down, and right here, when the pressure starts to rise suddenly, that's when the exhaust valve opens. And that's at 160 degrees. This is the known good engine. And this is the suspected bad engine, right about there. Actually, that's pretty close, about 160. So, is it possible that only the intake camshaft is off 1 tooth? I think we can pop the valve cover off, bar the engine over to where the marks are supposed to line up, and we can at least see by these marks right here. We should be able to see these. So this is exhaust. That one's supposedly on time. We can even count the links. We can count the links from here. 1, 2, 3, 4, 5, 6, 7, 8, 9 links from arrow to arrow. Let's try that. Alright, so according to the picture, the lines should be pointing at these castings, I guess, and the arrows should be pointing towards the links. And we need 1, 2, 3, 4, 5, 6, 7, 8, 9 links between the arrows. On the cams, we have dots instead of arrows, and we do have the lines. So I'm trying to line up. Let's start with the dots. So if my dot is here, 1, 2, 3, 4, 5, 6, 7, 8, 9, dot to dot. So is that correct? And then we can check the lines down there. So there's a line right here, and there's a line right there. Let me turn it a little bit more. I want to make sure that the intake and exhaust cam didn't get swapped around. The intake definitely has the reluctor wheel on it, so that's good. But we know the cam timing is off, and only on the intake side. So I really expected, if we count these links, 1, 2, 3, 4, 5, 6, 7, 8, 9. That seems to be on the money. How does that make any sense? So guys, this is really blowing my mind. I took out the crank bolt and aligned the keyway like this. It's vertical. And then used a borescope to make sure these pointers are pointing exactly at the notches there, and they are. They have 9 links between the 2 dots or arrows. Everything is adding up. How can this intake cam be retarded by 25 degrees physically? It's not making any sense to me. I even loosened up the bolt right here and tried to turn it by hand. The pin is fine. It's still locked to the gear. It's not like the pin sheared off and the camshaft rotated. That's not the case. Well, let me loosen that bolt again. We'll take a closer look. Alright guys, so I loosened this cam gear right there. Loosen that bolt up as far as it'll go up against the timing cover. See, the gear is loose on the shaft. Question is, the shaft right now is retarded. Can we advance it manually? No, it's trying to turn the gear. It's locked into the gear. The pin is fine. This is really not making much sense to me. Alright, so this is the known good Suzuki, and I got everything lined up. The crank, marked that at TDC. The arrows, these are original timing components. So the arrows have 1, 2, 3, 4, 5, 6, 7, 8, 9 links between them. That matches up. The lines are pointing kind of diagonally down. And for example, this notch on the CKP is pointing almost straight up. The single pulse right before the double pulse. R3 is right here. K. So I'm going to find some marks and see if the camshafts are exactly in the right position, because on the scope it showed that the intake cam was retarded by 25 crank degrees, so it would be about 13 degrees right here. So let me see where the R3 and the K are, where the lobes are, and we'll go from there. So on the BAD engine, here's a good reference. The tips of these lobes are in line with this little flat. That looks to be in the right position. Everything looks fine. On the known good, these 2 lobes are lined up precisely. Everything's identical. I mean, how can this camshaft on the scope be advanced? Let me put a screwdriver and make sure we're at TDC. Guys, these 2 engines are timed identically. Identically. The cam pulse right here, this one little notch, it's exactly the same distance as this one right here. See, it's a little advanced. So the reluctor isn't shifted, the camshaft isn't shifted. What? We're basing the position of the camshaft on our sensor. Well, this is an aftermarket sensor, and the other one I think is OEM, because that car hasn't been molested. So we can just put the other valve cover on this car with the other sensor and see if it runs any better and take the same scope capture. This is insane. Alright everyone, moment of truth. This one's put back together. We have the parts car cam sensor installed. I'm not going to scope it yet. I just want to see how it runs. Place your bets now. This is the last thing that could possibly explain our data. So it has to be the problem, right? Let's see. Okay, this one is possessed. This one's getting crazy. Let me throw a scope on it. See if the cam timing shifted compared to the known good. Same thing, it will not free rev above 1500 RPM. This is insanity. Alright, same 3 channels. Let's see what happens here. Roll the scope. Just want to let it idle, and it stalls out. It can't even run on 3 cylinders. Alright, so this is what we had before in this car with the aftermarket CKP. So we're at minus 17 degrees. Here's what we have now. Minus 25 degrees. 5, 6, 7, 8 degrees difference, but not 25 degree difference. And the spark timing is actually very close. So we're at minus 25 and minus 22. Let me open up the known good. Alright, so this is our known good. See the cam pulse is at minus 43 and the spark is at minus 25. The falling edge, that's when the spark occurs right there. You can actually see the little interference. Minus 43, minus 25, and this is with this car with the OEM CKP. We're at minus 25 instead of minus 42, so we're still 17, 18 degrees off, but the spark is occurring actually pretty close to the known good car. Why won't it rev? So this is where I tried revving it. Let's bring some cursors in here. Let's say that's 720. Look guys, that cam pulse is now minus 60 on a rev. How does the cam pulse move with respect to TDC compression? How do you explain that? But the ignition timing is minus 10 degrees at wide open throttle here. So this is wide open, there's no vacuum. So cam versus TDC here is actually quite interesting. You would think this would stay constant on a non-VVT engine, but it's not staying constant. Are we barking up the wrong tree? Can the compression peak actually shift? You know, this isn't like fast engine speed. It's just under more load. Can the compression peak be later by that much? This is nuts. Absolutely crazy. Actually, in the known good engine, if we measure during a rev, so right here, that cam pulse is actually about 60 degrees before TDC compression, just like on the bad car. That's known good. This is what we have right now during the rev. Minus 60, identical. So it looks like cam timing is on the money. There's no back pressure. Can it be bad fuel? Guys, they swapped injectors and fuel rails from that car, put it back on this one. It's not spark, it's not cam timing, it's not airflow. Do we think it's airflow? Fuel trims are fine. It's not trying to add fuel or subtract fuel. The air-fuel ratio sensor is doing its thing. This is actually really fascinating and frustrating at the same time. So my question is, what is happening at 1500 RPM? It's smooth. We're going to gently raise the RPM. Smooth, smooth, smooth. And then right there, right before 2000, you're going to start feeling a misfire. When you give it more gas, the RPMs actually drop. How do you explain that? We have to focus on ignition and fuel injection here. Smoothly, but right there, 1500 to 2000, it's hitting that wall and it's having a hard time breaking through it. If it does, it can actually rev up and get there. Just the most bizarre thing. This is insane. Alright, let's repeat the experiment with the pressure transducer on the other 3 cylinders. What if 2 of them are blocked somehow, which is completely bizarre, but I'm going to try it. Let's fire it up. Okay, so this is cylinder number 2. Don't see anything crazy, no high pressure on the exhaust. Same exact pattern. I moved the ignition probe to cylinder 2 coil. So cylinder 2 looks okay. I'm going to save this and do 3 and 4. Alright, here goes cylinder number 3. Stalls out. Nothing noteworthy about cylinder 3. Let's go to cylinder 4. Alright, cylinder number 4. Actually revved all the way through with cylinder 4 disconnected. How does that make any difference? We're down 1 cylinder and it revved all the way through. Huh. Looking at some basic OBD2 data. I don't know if it's running better or not. You have to full throttle it to get it through that wall. But it does go through it. We'll misfire right at the wall. If I punch it, it really bogs unless you're over half throttle. Oxygen sensors are fine, fuel trims are fine. We're just slowly letting it down. So 1500, it'll start to miss a little bit right there. Boom, boom, boom. Shaky, shaky. taking fuel away, minus 20%. Like right now, why is it misfiring when lambda is stoichiometric? See, the fuel trims went to 0. Here's the check engine light, I think, was about to come on. It was blinking. Not running like complete garbage now. I mean, I'm still flooring it, but at least it goes through the wall better than before. It's not stalling. Shut it off. Fires right back up. Runs smoothly. I think this system has an intake manifold runner valve. Let me make sure that's working. So I disconnected fuel injector number 4, and with light throttle, half throttle, we're getting through the wall. This is crazy. Now the wall's at 2,000 RPM. Let me reconnect injector number 4. It picked up cylinder 4 misfire. Probably shut it off. I wonder if, so you read fault code, it's still blinking pending cylinder 4 misfire. It's a clear fault code. Okay. Could it be that tuning valve that's stuck? It could be. That's the only thing they didn't swap. They told me the only thing we didn't swap is the intake manifold. Wouldn't that be funny? Because once we break through the wall, seems to be okay, but this wall, from 2 to 3,000. Timing's good, everything's good, fuel is fine, at idle it runs fine, at high RPMs it seems to be okay. It's just that transition. What if we unhook that tuning valve and maybe there's a bidirectional control? I don't know. So I unplugged that variable intake solenoid. Sure enough, it set a code right away. Let's see in actuation test if we can control that. It doesn't look like we can. Nope, that would be too fancy. We might have to manually energize it and see if it does anything.